All right, welcome back to Calc 2. I'm sorry it's been a while since I've been posting, and I've got a slightly different way of doing it now, so hopefully I can get caught up, and everybody will be good for finishing this out this way. So we're going to talk about 8.5 right now. Okay, this is going to be about probability. I'm going to go ahead and knock this down by one. Okay, and we have a little bit of a lecture to go through first, and then I will post some follow-up videos without going through the homework. All right. So first thing we're going to deal with, okay, is that we are going to constrain ourselves to, we're just going to be looking at continuous random variables. Okay, this is in contrast to discrete. So if you wanted to, if you're looking at like, what's the distribution of rolls you're going to get when you roll a dice, or when you roll 2 dice or 3 dice, or however many. These are counted up values. These are what they call discrete. Okay, you roll a die, you're going to get a 1, 2, 3, 4, 5, or 6. You're not going to get pi. All right. Whereas continuous random variables, these are things that are usually measured. Okay, so like times or speeds or distances, heights, weights, etc., things like that. So we usually can assume that they can fall between an integer value or between arbitrary values. Okay, it doesn't have to be integer. Okay, it could be fractions. It's okay. All right. So things that we usually deal with this like height, weights, speeds, time, distance, and proportions. Now we often model money as a continuous variable, even though it's counted, right? I mean, you can't go beneath, right, the penny, but it is, usually the values are high enough that this kind of gets washed out and we don't really have to worry about that. So the techniques we use, if we assume continuous, works really well for money, even though technically, right? We do it for finance and stocks. We assume that they're infinitely divisible. Now, your brokerage may not do that. My brokerage doesn't. You can buy 1 or 0. You can buy 2, but you can't buy a half. So, until the rest of my stock portfolio catches up, Google will be out of my range, because I can't buy one stock for Google. That's way too much. All right, so just to, gives you an idea of what we're talking about here. Okay, some notation. If I want to say, like, what if a person, we want to know the probability. A person is between 5'2" and 5'7". Okay, I'm going to convert them to inches. So we have 62 inches and 67 inches. We would write probability 62 x and 67. Now, one of the things I get asked you is, what's the value? What's the area under the curve for a single point? Right? It's 0. So does it really, numerically, does it matter if I put those in or not? It really doesn't matter. Okay. Modeling it, right? When we try to take the English and put it into a mathematical equation, this does matter. Okay, but it's more of an interpretation problem than it is a numeric one. Numerics, this is going to be, whether or not you're greater than or equal to, or just strictly greater than, it's not going to matter numerically, because really what you've got, right, is, if I wanted to do, like, if I wanted the interval between 0 and 1 and 1, we could write for some function, okay, defined on this. We would have to write something like limit, right, as a approaches 1 from the bottom of, we'll do 0 this way, that way I don't have to worry about 2 limits here, up to an a. Okay, so a is approaching 1 from the negative of this f of x, plus 1 to 1 of f of x dx. Right, we'd have to add these together. What's the integral, right, of 1 to 1 It's 0. Okay, so this limit as x approaches 1 or limit as a approaches 1 really might as well be 1. Okay, unless there's something weird going on here, right? If there was a problem, we would have to exclude it and get the limit as x goes to it. But for like a really well behaved function, right, the limit as x goes to 1, assuming the function exists there, right? And this is just going to be gone. All right, we're not going to worry about it. So if you have greater than or equal to, or just greater than, it's really, as far as our calculations go, this is not going to make that much of a difference. So, okay. That's how we write the probability that x is between 62 and 67 inches. Okay, that's what we want the probability for. All right, let's see here. Let's see. Yeah. So one of the things we could talk about, we're going to say x is a continuous random variable. F of x, right, is a probability density function, right? PDF for short, not that kind, the other kind. All right. Things that PDFs have to have. Okay, if f of x is a PDF, then it has to be bigger than 0. Right, it has to be bigger than 0 for all of the whole domain, and the integral of this thing, of f of x, right, this is the whole domain, because a to b is like negative infinity to positive infinity. Okay, this has to integrate out to 1. All right, that's how you tell whether or not something is a probability density function. Okay, so it has to always be positive or 0. Right, it can never be negative, and it has to integrate out to 1. Okay, over the whole domain. Now, we could restrict the domain. There's lots of PDFs that like go from 0 to 60 because maybe we're studying a time, or it goes from 0 to 12. Maybe we're studying a length. But the way we would write that, right, is like this is one of my favorite PDFs for doing basic stats, and that's to say something like f of x equals, right, 1/12 when x is between 0 and 12 and 0 everywhere else. Right, so integrating this thing out, do we really care about everywhere else, or do we just care about the 1/12 between these two? We just care about this part. Okay, so to test it out, right, we go from 0 to 12 of 1/12 dx. That's 1/12 x from 0 to 12. So that's 1/12, 12 minus 0, which is equal to 12 over 12, which is 1. Congratulations. A lot of times, see, in stats class, we draw this because this quite honestly freaks them out. Here's my x, here's my y. Here's my y is equal to 1/12. And you might at this point rightly be asking, like, couldn't we just look at the rectangle? Yeah, you could, which is why I like this as an example on basic stats, because they're rectangles. So there's nothing to be afraid of here. If I wanted to figure out, like, what's the probability, right, I want to know, what's the probability between, say, 3 and 7, okay? Then all we would do is we'd integrate out 3 and 7. We would want this portion, this portion of this whole rectangle. So probability, right, that's like the part of the whole. So it's this part of the whole thing. So we would just integrate that out, right? We go from 3 to 7 of 1/12 dx. I'll spare you the calculus, right? And we get 4/12, which is a quarter. Okay, no, it's a third, sorry. Okay, so you can do it with geometry, that's fine, right? 4/12, you get a third. Or you can do it with calculus, that's fine. But that's the kind of thing we're talking about. All right, now we're going to get more interesting shapes, so you have to use calculus to do this. But as a general, here's what we're talking about. Here's a basic idea of what's going on. Rectangles are wonderful tools to help us figure all of that out. all right? The other idea is to make sure that, again, I often forget to write down 0 else. We just write down this thing and say, okay, x is going from 0 to 12. And it's kind of understood that the function doesn't exist anywhere else. Or if it does exist, it's 0. And we'll be okay with that. Right, average. Okay. What's the average value? This is also called the expected value. And this is often abbreviated in statistics as the symbol mu. Okay, so if you studied biology at all and you used micrometers or micrograms, that's the same little u that's in front of the thing. So microgram, right, would be that. I know my mu doesn't quite look like the u that they use in biology. This is just how I write it, but feel free to write it any way you're comfortable with. Okay. I won't correct, well, something like a u or something like halfway between an m and a u is fine. Yeah, I'm not really correcting penmanship though, but that's what this is. All right, so that's called expected value. It's the average value. Okay, the mean. Okay, so lots of different words to describe what we're talking about here. And the definition for this is the integral of x times f of x for that PDF. Okay, and again, it's over the whole domain. Again, I wouldn't do all of this for that previous function because it only goes from 0 to 12. Okay, so if we wanted to do the previous one, right, that would be from 0 to 12. We would have x times f of x. Okay, so not really a terrible, again, rectangles. It's going to work out really well. So we get 1/12 x, right, dx from 0 to 12. Go ahead and integrate. We get x squared over 2, so over 24, and 0 to 12. Okay, so we would get what? We would get 12 squared over 24 minus 0, so this is going to be 144 over 2 times 12. So that's going to be, right, this is 12 over 12, so we just get 12 over 2 and 6. And I hope you would expect, right, well, it's halfway between 0 and 12 because it's uniform. Okay, if there's a big hump here, if it's not all the way across like this, then, we're going to get different values here because it's going to favor one side or the other. But for a flat distribution like that, it should be in the middle. Okay, so again, I hope I'm appealing to your geometric sense here, your geometric sense of your intuition. Let's see here. We could do a hard one. Okay. When I say hard one, I mean like, a hard one at this point in time. So if we have an f of t is equal to 0 when t is less than 0, and then we have a k e to the negative kt when t is greater than or equal to 0. Again, piecewise function. Okay, that's why we study them. They're being real formal about this. Usually people just write this and then they say t is greater than 0. Okay, if they're in a hurry, they don't normally write this all the way out. We will in textbooks, but if you don't, I'm not gonna, I'm gonna know what you meant by the other piece. All right. And let's find the mean of this thing. What is the mean? What is the expected value of f of x? All right. So what we're going to do is we are going to get e of x is equal to, or e of t in this case, right, f of t, is going to be the integral from 0 to infinity of k times t e to the negative kt dt. All right, so all we're taking is this function, and we're just multiplying it by a t. So look what we get to do. We have all the joy of an improper integral. We have all the joy of integration by parts, right? We're having more fun than we should really be allowed to have right now. Okay, so let's go through this and we'll try to be careful about taking care of all of this. And I have to watch my signs because otherwise I'll mess this up. Okay, limit, right? A greater, or A goes to infinity of 0 to A of k times t e to the negative kt dt. So we're going to do integration by parts here. Okay, so now integration by parts. Okay, and I know there's a tabular integration, and that's fine. If you want to use that, that's perfectly fine. Just be careful because it doesn't work in every case. All right. My elements of calc is why I don't teach it. It's because the elements of calc people they use it for everything. It's like you can't do that. Like I saw it online. The tutor told me. Like I know. That's why I didn't tell you. Okay. So u is equal to kt, right? Du is equal to k dt. dv is equal to e to the negative kt dt, and v is equal to negative 1 over k e to the negative kt. All right. You take this derivative, make sure that taking this derivative gets you back here, right? Because we're going to have a chain rule. K's are going to cancel, negatives are going to cancel, everything will be good. All right. And now we go ahead and employ our integration by parts. So this is going to be limit as a goes to infinity. All right. What do we have here? We have kt, right? That's my u, times my v, which is negative 1 over k e to the negative kt, right? uv, minus integral from 0 to a, right? That's going to apply to both of these. And we have negative 1 over k e to the negative kt times k dt. Okay? Just thinking it's been a while since we've done integration by parts. So I'm trying to go a little bit slow with putting all the pieces back in. That way we can follow along. All right. So we have limit as a goes to infinity. And we're going to clean this up, right? K over k is 1. So we're going to have negative t e to the negative kt, and we're going from 0 to a. Okay. We have a minus and a minus, so here's a plus. Integral 0 to a. That canceled. This cancels, right? K over k. And we just have e to the negative kt dt. That canceled off, and that's all we have left. Okay. So one more time, let's integrate this now because we can integrate this. As a matter of fact, we already have. Right? So negative t e to the negative kt, 0 to a, plus negative 1 over k e to the negative kt from 0 to a. Right? Everything's good so far. All right, so let's see here. Yeah, what happened to that negative sign there? Went away. Okay. So what I'm going to do is I'm going to flip my my limits because I'd rather not deal with the negatives. So this is limit as a goes to infinity, and this is t e to the negative kt from a to 0, plus, taking out that negative 2, this is 1 over k e to the negative kt from a to 0. Okay. All right. Let's plug in a, or let's plug in 0. All right. Now we can just deal with this at one thing. So we have 0 times e to the 0 times k, right? Plus 1 over k e to the negative k times 0. This was t evaluated at 0. Minus, and now we have limit a goes to infinity of a e to the negative k times a plus, right? We can do that. Okay, so same limit. Okay, same limit. 1 over k e to the negative k times a. All right. So this one's going off to infinity, but this is going to 0 faster. So that's 0, and that's just 0. So what do we have? We have 0, right? Because 0 times that, and 1 over k times 1 minus 0. This is equal to 1 over k. So the mean is 1 over k. Or k is equal to 1 over the average. And that's usually how you're going to see, this is called an exponential distribution. That's how you're going to see it. Okay, so if I go way back up here at the top, back up to here, right? The way they're going to write this thing is f of t, right, equals 0, right, when t is less than 0, and 1 over mu, e, right, remember this is mu, okay, e to the negative t over mu, right, when t is greater than or equal to 0. If you take a stats class, they're going to expect you to memorize this. I would not expect you to memorize this for this class, okay? If I want you to find, like, what's the average of the exponential function, I'm going to write this down, okay? I'm going to give you exactly the way that I pitched the problem to you right here is exactly the way you're going to see it on an exam. I don't expect you to memorize the names. I don't expect you to memorize the formulas, okay? It's just going to be find the mean of this function. The only thing you're required to remember is like, oh, that's right, it's x times f of x. It's the only thing you have to remember about this, okay? Never going to ask you, to determine whether something is or isn't a PDF, right? It's just going to be given to you as if it were. So that's just for context and the rest of the problem. It's not anything you have to deal with. Okay, now there is one major problem, and that is your book really likes the normal distribution. And I will warn you, we have a whole class in figuring out normal distribution stuff, and that's called intro to statistics. And if you think that those students have mastered calculus to where they're going to do this function as an integral, you have another thing coming. So the normal distribution, we'll use x, is equal to 1 over the square root of 2 pi sigma squared e to the negative x minus mu squared all over 2 sigma squared. I do not ever want you to use this formula, okay, to figure out any problems in the homework. You are not doing Simpson's rule on this thing. It is a complete waste of time, all right? There's a calculator button that will do this for you. I'm a little surprised that they didn't make this a little bit easier for you, because in statistics class, we use what's called a Z transformation. And we take all of our variables, right? We could have a mu and a standard deviation, and we map them into a distribution where the mean is 0 and the standard deviation is 1. So just taking, and this is a very simple transformation. It's Z is equal to x minus mu divided by sigma. All right, and this will give us a Z variable whose mu is, right, whose mu is 0 and the standard deviation is 1. If I take one standard deviation up, right, 1 over the mean, we're going to end up with just the standard deviations. Okay, so what this would end up looking like is a much easier function. Okay, so we would have to integrate 1 over square root of 2 pi e, right, because there's no sigma, sigma's 1. Okay, e to the negative x minus 0 over 2. Okay, this is called the Gaussian. And if you're going to go into electrical engineering, you're going to see this a lot because it has to do with a lot of signals. All right, but integrating this or doing doing our integration on this function is a lot easier because we can just hold this off to the side and just deal with integrating e to the negative x squared over 2. Okay. As a matter of fact, if you ever have me for Calc 1, I make you find the inflection points of this thing. So we can take derivatives of it real easy. You can't integrate this. Okay, I know some people will show you some little tricky tricks to add in like an extra variable in here. Technically, well, you can do it, but the traditional way of doing this is to map it to the complex plane and solve it that way. So it's a joy. But yeah, it's not the nicest integral to deal with. Okay, this is why we have tables for it. Okay, and again, that's why they want you to use Simpson's rule. There's actually a better way that we're going to learn at the end with series, and we're going to make a Taylor series out of this and integrate that instead. All right, this is not Simpson's rule. It's like, why did you pick that? This is like the worst thing. Numerically, this is a mess. So there, that's what we have. but yeah, you can't really integrate this. Yeah. So like I said, there's other methods to solve all of these problems. I'm going to go over them in the homework. Please spare yourself. Don't do this. Okay, this is not a good use of your time. And I hope I got some of you before you went off and did this. If I didn't, I'm sorry. I will tell you that it builds character. So my apologies if you did this problem, but you know, you can yell at me for that. That's not something I wanted you to ever do. All right, I'm going to stop here. We're going to do some homework problems. I'll go through the demonstrations. I'm going to break them up into stuff that isn't normal and stuff that is. Okay, that way we can isolate this problem. All right, so I'll see you in the next video, and take care, and I'll see you then.